Welcome and hello. This is a video lesson in the FHWA hydraulic toolbox. And in this lesson, we're going to be talking about the Bridge Scour Calculator, specifically the first method, which is long-term degradation. So if you've been following along on previous lessons, we talked about an introduction to Bridge Scour Calculator, which is lesson 19. And then in lesson 20, we did a quick demo in HEC-RAS to define the bridge geometry and the cross-section geometry. All right, so I'll go ahead and link those two lessons in the description if you're interested. Let's go ahead and get started on the long-term degradation. Over here in my project, I have a Bridge Scour Calculator. So I'm going to go ahead and open that up just by going right-click, Bridge Scour Analysis. And then right here, this long-term degradation is the checkbox I'm going to check. Click on Define, and this is the user interface we're going to be discussing in this lesson. Before we can do this, I'm just going to go ahead and back up real quick and give a quick introduction on this long-term degradation. The limit of long-term degradation at a given channel location is typically the lesser of two different degradation calculations, that calculated based on armoring or the equilibrium slope method. At the top of this dialog box, we have input data, and then down below, we will have results once the appropriate input data is completed. All right, let me go ahead and just back out real quick and first add a geometry. So enable scour plot options, click this checkbox, click on import. This is now where I need to browse for my HEC-RAS file. So click on browse, click on project. All right, and then I need to set the cross section, which I covered in those previous two lessons, specifically lesson 20. And my bridge is at River Station 300. Okay, so I have an approach cross section at River Station 600, the bridge cross section at River Station 400, and then the actual bridge is centered at River Station 300. One more thing I have to do here is set the abutments, and I am good to go. All right, so click OK to that. Again, if you're interested in the HEC-RAS, this is the file that I'm working with here. I have a bridge that's defined right here, and I've already ran a simulation which is showing the results right here with a flow rate of 2000 CFS with the water surface down here and a flow rate of 7000 CFS with the water surface further up here. All right, so let's go ahead and get back to the hydraulic toolbox now. After importing that HEC-RAS project, it automatically checks all of these checkboxes on. Actually, the one I want is long-term degradation. All the others I'm going to just uncheck for now. So I'm not focusing on those. And let's get started here. I'll click on Define under Long-Term Degradation. The first method is armoring. The second is equilibrium slope. Start with armoring here. Armoring occurs when the hydraulic forces are sufficient to move a portion of the bed material, but insufficient to move the larger sizes of material. Under these conditions, the smaller material is transported and removed from the bed, leaving the coarse material, or what is called an armoring layer. The user's manual brings up this bridge scour components. These are the four components, and then the long-term degradation discussion begins here on page 70. This is chapter 15.1.2.1, long-term degradation. Okay, this is just the overview. I'm sorry, let me scroll down here. I have page 78 in my notes. Okay, so here's 78. Here we go, 15.3, Bridge Scour Calculator, Long-Term Degradation. Part 1 is armoring, and then the second part is equilibrium slope. In both situations, what we're doing is calculating the depth of the degradation. This first equation right here, which is in the hydraulic engineering circular number 20, equation 6.13, we'll get to that in just a moment. This first equation calculates the critical sediment size, D sub C, which is not transported. So every sediment size smaller than D sub C will be transported and contribute to the degradation. But sediment sizes larger than this D sub C and equal to D sub C will not be transported. So it's sort of a critical or a threshold grain size diameter. And then further down below here, this second equation is calculating the USBR depth of armoring, Y sub S. So under the clear water conditions, which is a conservative assumption, typically it is equal to 1 to 3 times the critical size, with at least 2 times the critical size required for stability. All right, so let's check out these equations and the exact parameters in the hydraulic engineering circular number 20. You can download this document here with a link in the description. I'll go ahead and leave that. But here is the D sub C variable, and this is the bottom of page 196, top of 197. D sub C is the diameter of the sediment particle at the critical condition. And then we have a few other terms here. So tau naught is the boundary shear stress. Gamma and gamma sub s is the specific weight of the water and the sediment. And then finally, K sub s is a dimensionless coefficient often referred to as the Shield's number. What it tells us further down is that the Shield's number parameter can range between 0.03 and 0.1 for the natural sediments based on particle shape, angularity, gradation, and imbrication. The use of 0.047 for sand is typical, but if you're using a larger sediment, 0.03 is what would be used typically for gravel or cobbles. All right, so let's go back to the calculator and start adding some numbers. The first term here is Shield's parameter. I'm going to type in 0.047, so we'll just assume it's that typical sand value that was mentioned. Next up is the hydraulic radius and then the average channel velocity. So this is sort of where the HEC-RAS results come into play. You can just make up numbers if you're learning the software, but if you've actually ran a simulation, you can go to your View, Profile Summary Table. This is the results for my Profile 1 and Profile 2, which is my 2000 CFS and 7000 CFS steady state 1D results. I'm going to remove channel velocity and then add a column for the average velocity and what was it, hydraulic radius. So I know this is a little bit of a HEC-RAS demonstration, but it'll be over soon, so just hang with me here. I'm going to scroll over to the far right column. I'm going to remove column 10. I'm going to search for velocity now, average velocity of flow in the total cross section. So we'll double click that. And then I want hydraulic radius. So we'll search for radius. And then this one right here, hydraulic radius for the cross section, both with 2 decimal place precision. That should be sufficient. Upstream of the bridge is right here. So the hydraulic radius is 4.01 and 5.13 for my 2 different profiles of 2000 CFS and 7000 CFS. And then the average velocity in the entire cross section is 6.85 and 9.33. That's in units of feet per second for my 2 different flow profiles. All right, so let's just go ahead and start with the 7000 CFS flow first. Go back to my toolbox. I said the hydraulic radius here was 5.13, and then the average channel velocity is 9.33. That's in units of feet per second. Okay. Here are a couple other terms that we saw from the equation: unit weight of water, unit weight of sediment, coarse bed material. We'll go ahead and check that on. And then we'll just make up a D84, how about 100 millimeters? And then the armor thickness factor, our options are 0, 1, or 2. So now that we have this data entered, we have some of our results. The D sub C value right here is 0.3499, so 0.35 feet, which comes out to about 4.2 inches. So basically under these flow conditions, all of the sediment that's smaller than 4.2 inches will erode or be transported away. We also have a value here for that boundary shear stress. And then if I maybe change the parameters, so let's use the 2000 CFS numbers. I'll change the hydraulic radius to 4.01, tab off, and then the average channel velocity of 6.85 and tab off. And now the critical bed material has changed from 0.35 down to 0.214. So now it's just 2.6 inches. And of course, the shear stress has changed as well. Next, what we want to do, if we identify the percent of the bed material that's coarser than the critical bed material, i.e. D sub C, then it will also calculate that depth. So if I say 100, then it should be no depth of degradation. That makes sense because if 100% of the sediment is the critical bed material size or larger, then we're going to have a 0 degradation. That's effectively the channel bed is already fully armored. But if I say something like 50%, I'll type in 50 and then tab off. Now 0.43 feet is the depth of degradation, and the armor thickness is 0.43 feet. That makes sense. Okay, let's go ahead and just say 80%. So that means there's less degradation. But if I say something like 20%, that means 80% would be degraded. 1.71 is the depth of degradation. It looks like the armor thickness remains constant there at 0.43 feet. All right, so that is the controlled by armoring method of long-term degradation. Again, we need to compare this depth right here of 1.71 feet, or whatever your numbers actually come out to, with the other method, which is controlled by equilibrium slope. When water is released from dams or detention ponds, downstream channels tend to degrade until shear stress is too low to mobilize the bed. In sandbed channels, this can cause significant degradation, but less degradation occurs in gravel bed channels. So there's actually four different methods. We first need to select this slope equation, either no sediment supply using Shields criterion. No sediment supply is considered the clear water source, so there's no sediment in the inflow. The next method down also uses no sediment supply. That's just a different equation, Myers-Peter-Mueller. And then there's also reduced sediment supply and also sediment transport equals sediment supply. So let's just go ahead and look at the first one. If we go to the user's manual, this is on page 79. Here it is, equilibrium slope. It talks about four different methods here, and this equation here is the first method, which is the Shields method. As is the case, the user's manual doesn't provide quite enough detail to fully understand it, in my opinion, if you're brand new to the topic. But this also comes up in the Hydraulic Engineering Circular 20 on page 199. So here we go. Equilibrium slope analysis. Here is that same equation. This is the Shields equation. And if we scroll down a little further, here's the equilibrium slope for the second method, the Meyer-Peter-Mueller equation. And then I found the reduced sediment supply equation 6.23. That's right here. So there's the equilibrium slope calculation. And for each of these calculations, the parameters are listed down below and described in the text. But to keep this example and this lesson fairly simple and straightforward, I'm just going to use the no sediment supply Shields equation, which is this one right here. And the downstream degradation is a function of the slope times the distance from the base level control point to the point of interest. All right, so let's go back to our calculation now. We're selecting Shields. That's cool. D90 is the first parameter that we need to insert. We just need to make up some numbers here. I'll just say D90 is 50 millimeters. Shields parameter, I'll just go with the same 0.047, which is typical for sand. Manning's N value, I'll say is 0.035. Discharge per unit width. Okay, so the units here is in CFS per feet. This is sort of like average velocity or hydraulic radius. It's something that you should be able to get from your model results. I could just go to the cross section of the bridge itself. And then at 2000 CFS, that is, I'll say a width of 60, at least the top width of 60. And then at 7000 CFS, that right there is a top width of 122. Actually, I think I do have that listed in a table. Yeah, top width right here. So 54 and 101. My notes give me a discharge per unit width of about 33 and 56. I may be using slightly different numbers, but let's just roll with that. So for the 2000 CFS flow profile, I'm going to say 33 CFS per foot. For the current slope, I'm going to say that's 0.01, and then that's in a decimal. And then this last parameter here is the distance from base level control to the point of interest. So I'll go ahead and just say 30 feet. All right. So when I go ahead and make that calculation, it shows me the ultimate degradation amount. This is the depth. It's 0.23 feet. So that's quite a bit less than the armoring degradation of 1.71 feet. Let me go back to equilibrium slope. This time, let's change some numbers. Let's increase that discharge per unit width from 33 up to 56. And if I tab off, degradation is still low, 0.25. Okay, so let's increase the distance. So instead of 30, we could increase that to say 100 feet. And then boom. Now the degradation is only 0.85 feet. So still a fair amount less than what we calculated when controlled by armoring, 1.71 feet. All right, so one last thing to mention on controlled by equilibrium method is that based on the slope equation you use, whether it's Shields or Meyer-Peter-Mueller or reduced sediment, you're going to have different input data because there's simply a different equation that governs and calculates the depth of degradation. Some of them are still the same. For instance, the distance upstream of the base level control and the current slope should exist in all of these methods. Okay. There's also user specified scour depth. This method is not discussed in the user's manual because it's simply a way to keep track of that scour depth if you happen to calculate it external to the hydraulic toolbox and you just wanted that number in here for your records. Okay. So if you click OK and then click on the Bridge Scour Summary table, it shows the user specified scour depth. Okay, let me change that back. All right, so I'm going to switch it back to controlled by armoring 1.71 feet. Click OK. Click on Bridge Scour Summary table. And now under long-term degradation, we have 1.71 feet controlled by armoring. That is it for the Bridge Scour Calculator with regard to long-term degradation.